In the chem activity number 13 and the corresponding videos, we're going to revisit acid-base theory. In particular, we're going to look at the meaning of pKa. We're going to look at using curved arrows to show electron movement in an acid-base context. And we're going to be looking at comparing the relative acidity and basicity. Now, at the very top of the page in this activity, I remind you about something. I indicate that a thorough understanding of acid-base chemistry is a prerequisite to understanding most aspects of organic chemistry. You might have thought you left acid-base chemistry back in first year. However, organic chemistry involves a whole lot of acid-base chemistry, but from a different perspective, and hopefully you'll find that once you master these tools, you'll feel confident in predicting a lot of outcomes in organic chemistry. Back to things, though, that you're maybe more familiar with. So let's take hydrobromic acid, let it react with water. You may in fact remember that hydrobromic acid is a strong acid. So although I'm showing this as equilibrium arrows, we typically think of this as occurring essentially in one direction and 100%. Now we rely on the Bronsted-Lowry model of acid-base chemistry, and Bronsted-Lowry model tells us that an acid is something that donates a proton and a base is something that accepts a proton. And therefore we would consider the HBr as being the acid as it donates a proton to the base water. Now one of the things about the Bronsted-Lowry model is that we also look on the other side of the reaction and look at the products and consider, well, what if the reaction could go backwards? In terms of going backwards, the hydronium ion is considered to be the acid and the bromide is considered to be the base. So in the Bronsted-Lowry model, we label things that typically, for instance, in the Arrhenius acid-base model, you wouldn't label as being an acid and a base. In particular, you wouldn't be labeling water as a base and you wouldn't be labeling the bromide ion as a base. So these are things that were covered in first year. Now in organic chemistry, fortunately, we still deal with Bronsted-Lowry acids, and HBr is still an acid and H2O is still a base. But we also want to think about, well, what's happening here? What does it mean for an acid to donate a proton? And we use the curved arrow notation, as in the reaction mechanism curved arrows, to show in a sense the transfer of a proton and the progress of the reaction. And rather than write out all the lone pairs, we write out the necessary lone pairs. So I've rewritten the reaction at the bottom to show you a perspective that an organic chemist might take. So for instance, the organic chemist would look at the base water and say, okay, it's got that lone pair of electrons on the oxygen, and that lone pair will react in a sense with the proton and make a new bond to that proton. And as a result, the bond between the hydrogen and the bromine will break. And in a sense, that will release the bromide ion. Note we don't bother writing all the lone pairs and things in our products because indeed we know that they're there. So that's an important difference in thinking about this reaction in terms of organic chemistry. Now one of the things that was introduced in first year is this idea of conjugate acid and conjugate base pair. And so while in the overall reaction I've labeled HBr as an acid reacting with water as a base, we can also talk about the fact that HBr has a corresponding conjugate base, and its conjugate base is the bromide ion. So it's not that HBr reacts with bromide, but rather when HBr donates its proton, the resulting base is the bromide ion. So a conjugate acid-base pair differ by one proton. In a similar fashion, we can talk about the hydronium ion as being a conjugate acid. Now this is thinking about the reaction in the backwards way, and its corresponding conjugate base is H2O. Again, the concept of conjugate acid, conjugate base is also incredibly important in organic chemistry. So now we ask you to use the organic chemistry approach to thinking about these reactions and explore the reaction between ammonia and water. So we ask you to use the curved arrow notation to show the movement of electrons. Also label the acids and bases on both sides as we did in the previous example, and indicate the conjugate acid-base pairs. You may wish to stop the video while you do this. So first of all, what might be helpful is to actually label who are the acids and who are the bases in this reaction. So starting on the left-hand side, in fact, it turns out that it's water that's acting as the acid. It donates a proton to the ammonia. And so I'm going to label the ammonia as our base. And on the other side, it's the ammonium ion that's acting as the acid and the hydroxide ion that's reacting as the base. Now back to the left-hand side then, it'll be our base with its lone pairs of electrons that'll be picking up the proton. So the acid donates the proton, but in order for an acid to donate a proton, we need a base to be able to pick it up. And we show the curved arrow of that base picking up the proton. Now, one of the things that students struggle with at first in showing the curved arrows is they may initially start with the lone pair of electrons on the nitrogen and grab the proton, and then they leave it at that. But we also need to show that this bond gets broken. And just to be clear, I want to make sure that my curved arrow starts actually in the middle of this bond and points at that oxygen. So that's using the curved arrow notation to represent this reaction. We've labeled the acid and base on both sides. Now let's label the conjugate acid and the conjugate base pairs. So we start with the conjugate acid H2O, and its corresponding conjugate base would be the hydroxide ion. We start with the ammonium ion, and its conjugate base would be the ammonia. So hopefully these things feel relatively familiar to you, with the exception, of course, introducing the idea of using the curved arrow notation to represent these reactions. Here I'd like to review a little bit thinking about Ka and pKa. So I have two representative reactions of acids reacting with water. Perhaps you remember hydrochloric acid as being a strong acid, and as such you know that its reaction more or less goes 100%. You may recall that we labeled acetic acid as a weak acid, and this means that its reaction only occurs partially. There's a partial ionization, there's a partial donation of the proton, and often for this sort of weak acid involving a carboxylic acid, we say the reaction goes about 1%. Now we can reflect really the degree to which these reactions go by looking at the Ka and the pKa. Now very roughly, a Ka essentially is the concentration of the products, so the hydronium ion times the chloride ion, over the concentration of the reactants. Now for Kas, we do not include water as part of the reactants. Its concentration essentially doesn't change, so the reactant's concentration would be HCl, or the acetic acid in this case. But the main point is it's really a ratio of product over reactant, and the more the reaction goes, the greater the degree to which the reaction goes, the more product it'll form, therefore the larger will be the Ka. Now for HCl, normally it's considered that its Ka is roughly 10 to the 7. And in the case of acetic acid, we say its reaction goes roughly 10 to the minus 5. Now P, as in pKa, means the negative log. So pKa is equal to the negative log of the Ka. So if we take the negative log of 10 to the 7, we end up with minus 7. If we take the negative log of 10 to the minus 5, we end up with 5. So these are two values that indicate relative strengths of our acids. Negative values for pKa's generally represent strong acids, and you'll see that part of the strong acids will include things like nitric acid, sulfuric acid, hydrobromic acid, hydroiodic acid, and they will all have negative pKa's. Weaker acids will have positive values, again because of the negative log function. And you'll see that we'll be looking at ranges from 1 through to 5, but actually as high as 10, 20, 30, 40, and 50. So the range of the different kinds of acids that we'll be looking at in organic chemistry is quite a bit more broad than what we looked at in first year. Now a little bit more about what pKa's tell us about the nature of an acid. So here I represent a generic formula for an acid, so simply HA, reacting with water. And I would like to remind you that when we say Ka, what we mean is the acid reacting with water. So that's different than K equilibrium, which can be any kind of equilibrium reaction. In this case, it's the acid with water specifically. So HA as an acid reacting with water will form the hydronium ion and the corresponding conjugate base. Now, the next point is actually incredibly important. The pKa of such a reaction tells us two important things, and I really encourage you to try to master these two important things. Clearly, the pKa is first of all going to tell us the relative strength of an acid, how well the acid donates a proton, or how easily a proton can be removed from that acid. Again, the smaller the value of the pKa, the stronger the acid. So negative pKa's mean a really strong acid. But in the same way, a pKa also tells us something about the stability of the corresponding conjugate base. And so the idea here is, if this reaction that we've just shown goes really well in the forward direction, so let's say it's like hydrochloric acid, where we've got a pKa on the order of -7. Well, what it means is that the reverse reaction doesn't go very well. And if the reverse reaction doesn't go very well, well, then it tells us that the A negative, that conjugate base, is quite stable. And so a pKa, yes, tells us about the forward reaction, but it also tells us about the reverse reaction. If the reaction goes very well in the forward direction, it goes very poorly in the backwards direction. So we could do something like this, just to remind ourselves that, yeah, if something goes very well towards the right, it doesn't go very much towards the left. So we say pK indicates the relative stability of the conjugate base. And if something is stable, it doesn't react very well. It doesn't do its job very well. Or you can also think of it in energetic terms. If something is relatively stable, it means it's of low energy, and it would require a lot of energy to change it back or cause it to react. So keep these things in mind as we go forward and look at other things. So I ask you to complete the following statements. So as we were alluding to, the greater the pKa, the weaker is the acid. So if you have a pK on the order of 20, 30, 40, 50, you're going to get a really weak acid. And again, the greater the pKa would mean the less stable is the conjugate base. If you have a weaker acid, well, to some degree, the conjugate base will be formed, but that conjugate base would be highly reactive, and the reverse reaction, in a sense, would be favored, and we'd form the acid again.